That is our power engineering topic. Okay, and we have discussed about the simple vapor power cycle and also ideal Carnot cycle. And we'll continue with the our Rankine cycle point. Okay, quickly I will give explanation about the Rankine cycle, that TS diagram. Okay, so those yesterday who have missed this lecture, they will understood the Rankine cycle also. Okay, so look at this diagram. As we know that there are four processes are there. 1 to 2 is the isentropic compression in pump. 2 to 3 is the constant pressure heat addition in the boiler. Then 3 to 4 process is the isentropic expansion in the turbine. And the last one, fourth one is the heat rejection in the condenser. Okay. So if you look at the diagram, at pump, water enters in the pump at state number 1 as a saturated liquid. That water will be as a saturated liquid and is going to compress isentropically, okay, to the operating pressure of the boiler at hot pressure to the operating pressure of the boiler. Then the water temperature slightly decreases, okay, in the specific volume of the water. Okay, so water temperature is going to decrease, okay, in that specific volume of the water. Then the vertical distance between, if you see in the diagram also, in a TS diagram, the vertical distance between the state 1 and state 2, okay, state 1 and state 2 on this TS diagram is greatly exaggerated for the clarity only. Okay, if water were truly incompressible, would there be temperature change, okay, at all during the processes? Okay, so that question maybe rise. Okay, so here that process 1 to is the isentropic compression in the pump. Then water is going to enter in the boiler, okay, at state number 2. Okay, now this water is a compressed liquid at state 2. Okay, and then after this boiler at state 3, we'll get the superheated vapor at state 3, because in the boiler we are taking heat from the external source. That means heat addition happens in the boiler, so that saturated liquid or compressed liquid is going to convert into the superheated vapor form, okay, at state number 3. Okay, so here heat addition is there, and that process is constant pressure process. Okay, now as we know, the boiler is basically large heat exchanger where heat originated from the combustion of the gases in terms of, we can say, furnace or the nuclear reactor or the other sources, okay, where that heat is going to transfer to the water, and which is essential at constant pressure only. So we are getting that line from 2 to 3. So you can see here in TS diagram also we are getting this line. Okay, just I have shown this line is a constant pressure line. Here heat addition is occur in the boiler. Okay, now the boiler and together with the section where steam is superheated. Okay, so it is called superheater also. That boiler, so it is called superheater or steam generator. Now at point 3 or state 3, we are getting the superheated vapor at state 3, and that is going to enter in the turbine. Okay, that is going to enter in the turbine where it expands isentropically at state 3. Superheated vapor is going to enter in the turbine, and that is going to expand isentropically, and it will produce work by rotating this shaft. Okay, by rotating the shaft which is connected to the electric generator. Okay, where we'll get the power or we'll get the output work. Okay, then the pressure and the temperature of the steam, this, okay, so the pressure and the temperature of the steam will drop during this process. Okay, temperature and pressure is going to drop during the process 3 to 4, that is isentropic expansion. So you can see in this diagram also. Okay, we are getting the vertical line but in downward direction. That means temperature and pressure is going to drop, okay, during this process. Then steam is usually will get as a saturated liquid vapor mixture, because this is the condensed steam. Okay, it is saturated liquid vapor mixture with a high quality. High quality means a drainage section. Okay, so steam is going to then condense at the constant pressure. Okay, at state number 4, steam is going to condense at condenser. Okay, in this condenser. Okay, at constant pressure. So process number, this last four to one, constant pressure. Okay, condensation means what? Heat rejection in the condenser. Okay, so here heat rejection will occur and we'll get the liquid or only saturated liquid, and that saturated liquid again back to the or return to the pump at state number 1. So this total cycle will complete. Okay, so in condenser, I repeat, in condenser, by rejecting the heat where to the cooling media, that saturated liquid vapor, okay, that saturated liquid vapor mixture is going to convert in the form of saturated liquid only, and that is going to enter in the pump, okay, at state number 1. Okay, now if you take the example also, that okay, understood. Now let it be. Now remember, if you see in the TS diagram, now remembering that this area under the process under this curve TS diagram will represent the heat transfer for internally reversible processes. Okay, so here you will get the area where I have shown that Q in, that is the heat transfer for the internally reversible process. Also we see that area under process 2 to 3, this area under process 2 to 3. Okay, it represent the heat transfer to the water in the boiler. Okay, and the area under the process 4 to 1, this 4 to 1, it is a, it will represent the heat rejection in the condenser. So the difference between these two processes, that means the area enclosed by this cycle curve, is the net work produced during the cycle. Okay, Q in and Q out. Okay, as well as you can consider the WP and WT also. So by considering this area under this curve, you can easily calculate the net work produced. Okay, so this is about the Rankine cycle. Okay, now we'll proceed for the further point, that is the energy analysis of ideal Rankine cycle. That means the further part of this Rankine cycle. Now we understood the this TS diagram and the working of this Rankine cycle. Now we'll calculate the efficiency of this ideal Rankine cycle. Okay, so that is the energy analysis of the ideal Rankine cycle. Okay, understood? Okay, say yes or no in the comment box so that I can proceed for the further part. Okay, okay. Now no problem. Now I will start the energy analysis of the ideal Rankine cycle. Now we know the TS diagram. From that TS diagram, we need to go for the energy analysis. Now, as we know that all four components associated with the Rankine cycle. Now, all four components means what? That pump, then boiler, then turbine, and then condenser. These are these all devices are the steady flow devices. Okay, all four components of the, or all four components which is associated which are associated with the Rankine cycle are the steady flow devices, and thus all four processes that makes up the Rankine cycle can be analyzed as a steady flow process. Okay, so this Rankine cycle I will or I can say these all four processes I will assume that are working in the steady state only. Okay, now the kinetic and potential energy changes of the steam are usually small relative to the work and heat transfer term. Okay, if you consider the what are the work produced or work transfer and what are the heat produced or heat transfer, with comparison with this, what are the kinetic energy or potential energy is there in that change? It is negligible. So here first assumption is that we have to neglect the kinetic energy and potential energy change in during this process, that is neglected. So the steady flow energy equation. Okay, we know that from the thermodynamic subject, steady flow energy equation. Again, I'm considering this steady flow energy equation per unit mass of the steam. Okay, and that steady flow energy equation I will reduce to the q in minus, here I have given the equation also. q in means what? What are the heat addition in the boiler minus heat rejection in the condenser, q in minus q out, plus what are the work input to the work input to the pump and work output in the turbine, that is a q, so w in minus w out. Okay, is equal to our enthalpy at exist. Okay, enthalpy at outlet we can say, or at exit, minus enthalpy at inlet. Okay, so He minus Hi. Okay, this equation we got from the steady flow energy equation. Okay, by neglecting the by negligible by neglecting the kinetic energy change and potential energy change. Okay, now as we know that the boiler and the condenser do not involve any work. Okay, because in boiler we are taking the heat and in condenser we are rejecting the heat, so it does not involve for any work. And the pump and the turbine are assumed working at a isentropic process. Okay, pump and turbine both are working at constant entropy, that is the isentropic process. So this conservation, so from the conservation of energy, okay, in relation to the each devices, okay, in relation to the this all four devices, I can consider that q of that pump I will consider as a 0. And what are the change, that means the at pump, okay, w pump, I will consider h2 minus h1. Here I have shown in the diagram also. Okay, h2 minus h1, this is our wp. Then again, by simplifying using the thermodynamic relation, I can say the small the v, that means the specific volume, in bracket p2 minus p1. Okay, that means the pressure at state 2 and at state 1, p2 minus p1. So we'll get the, from that formula we'll get the wp, that means the input work at pump. Okay, then again, if during the calculation or during the problem solving, that w1, sorry, h1 you have to take as the hf. Okay, saturated liquid, no? So hf at what pressure? At p1 pressure. And your specific volume, that means the v, you have to consider the specific volume at state 1, that is a v1. Okay, or you can consider the vf at pressure p1. Okay, here I have shown also at boiler we have to consider the no work, because there we have taken only heat, so w at boiler to 0. But here we have considered heat addition, so that heat addition using this formula I can consider h3 minus h2. Okay, then at turbine no heat addition or heat rejection, so q will be the 0. So we are getting only work output, and that is also process 3 to 4. So h3, so h4 minus h3 minus h4. Here h3 value is high, so I have considered at first. Okay, then at condenser no heat oh sorry, no work is produced, only heat rejection occurs. So W is equal to 0, and that heat rejection I can consider H4 minus H1. Okay. Now by putting this all in the steady general equation of the steady flow energy, we can reduce that equation as a W net is equal to Q in minus Q out, or you can consider as a WT minus WP. Okay. Now we know the input of the cycle as well as the output of the cycle. So I can say output of this cycle. Okay, for calculation of the efficiency, I can consider W net is the output divided by input means what? Heat input, that means heat addition in the boiler, that is a QN. Okay. Now W input means what? The W net means what? WT, that means the work done in the turbine, that is a W turbine minus work input at pump WP. Okay, and divided by the QN. Okay, so using this formula, you can easily find the our thermal efficiency of Rankine cycle. Okay, in the steady flow energy equation, I have considered some assumptions, and by reducing that equation, I have calculated efficiency of or thermal efficiency of Rankine cycle. Efficiency formula is very easy. Output divided by input. Output means what? Whatever the net work output, net work done. Okay. Divided by input means what? Our heat addition. Okay. So here we'll get the formula for the thermal efficiency of Rankine cycle, and this is important. Now, by looking to the diagram also, we can calculate the thermal efficiency of the Rankine cycle. That means by taking the ratio of area enclosed by the cycle on the TS diagram to the area under the heat addition process. Okay. So we know the integration. So in that again integration, we are considering the summation of areas. Like that, from the TS diagram, if you consider the ratio of area enclosed by the cycle on the TS diagram divided by area under the heat addition process only. From this also we can easily calculate the thermal efficiency of the Rankine cycle. Okay, got it? Now I will give 1 minute for you. Please write down the this equation only. Okay. From this slide, you write down the Q or from this slide you can write down everything. No problem. Steady flow. This is important to solve the gate problem or IS problem. Okay. Please write down this. This Rankine cycle energy analysis already you learn in the ATT subject. Same point, same concept. I have repeated here. Okay. Please write down. Say yes or no, whether you are writing or not. Okay. In comment box, you just mention yes, okay, written or writing. Okay. Because this formula is important. Huh? Sometimes in a GATE exam, they may ask to calculate the work done by the turbine or in the turbine, or what are the heat input in the turbine in the boiler, or heat rejected in the condenser, or heat or work input in the pump. So during that time you need these formulas. Now that that point 1, 2, 3, 4. Okay, I mentioned here. But sometimes in the gate problem, they may give the this diagram, but same that curve will be same. But the point that means 1.1, 2, 3. They may mention in different way. No problem. Okay, that means they may consider process 3 to 4 as a your process of heat. Sorry, your isentropic process at pump. Okay, so that notification, no no problem about that. Okay, but your pattern of curve should be same. This is standard. You go anywhere, okay, in IIT or anywhere, okay, the pattern of this rank and cycle will be the same, but notification may be changed. Huh? Have completed so that I can proceed further. Say done or completed. Total 55 students are there, and only two or three students are saying yes or no. Uh, what I should assume? Whether other students are in sleepy mode? Please wake up. Okay, now I will move on further. Once again, I repeat, this slide or these formulas are very important to solve our further problems. I repeat, on this TH diagram, only the pattern of curve. There is one question which is asked in the GATE as well as the IS. Okay, that I am going to take now. Okay, so you will get the importance of this TH diagram as well as this formula also. Okay, now I will proceed further. Now, normally the conversion efficiency of the power plant. Okay, this rank power plant working on the thermodynamic cycle, and thermodynamic cycle means what our uh, Rankine cycle. Okay, so the conversion efficiency of power plant in US. Okay, normally they are expressed in terms of heat rate. Okay, now normally the efficiency were finding in terms of percentage, but in US they are expressing this conversion efficiency in terms of heat rate, and that heat rate means what, which is the amount of heat supply, and that is in BTU unit. BTU unit. What are the heat rate or conversion efficiency is there in US? They are expressed in terms of heat rate. Okay, in the unit BTU. Okay, BTU is what, to generate the 1 kilowatt hour electricity. Okay, so the smaller will the heat rate, the greater will the efficiency. Okay, that point you have to consider, because by considering that 1 kilowatt hour is equal to 3412, okay, 3412 BTU, and by disregarding those losses, small what are the losses are that we are negliging, okay, which are associated with the conversion of the shaft power to the electric power in the power generator. Okay, that we are going to neglect, and by taking the relation between the heat rate and the thermal efficiency, we can express the equation for our efficiency. That is our thermal efficiency as a eta TH. Okay, okay, is equal to 3412 divided by heat rate. Okay, so this is one formula. This formula may be useful in some question. For that purpose, just I have inserted in this slide. So you can just note down the formula. Okay, if sometime they will give in heat rate, that time you can easily calculate the thermal efficiency using this formula. This 3412 value is means what? Generation of the 1 kilowatt hour electricity. Okay, there are the heat rate. Okay, now we'll start the. Now once again I repeat, this is a ideal Rankine cycle for the vapor power cycle, or for steam power plant or thermal power plant, and this is modified or by implementing some assumptions in the Carnot cycle. We have modified the Rankine cycle. Okay, so again, to make it possible in practical, we have to assume some points also. So now I will show the what will the actual cycle of actual pattern of this Rankine cycle. Just as we have learned ideal Rankine cycle. Okay, if we will go for practically or in actual case, the pattern of this Rankine cycle in the TS diagram, it slightly changes. And that I am going to show here. Okay. So next one is the actual vapor power cycle or actual Rankine power cycle. Okay. Now here, I, this actual vapor power cycle is differ from the our ideal Rankine cycle. Okay. So you can see here in the diagram number 1, that is the A. Here you can see it is slightly changed. Okay, this is a TS diagram. Okay, in ideal cycle, we are getting point number 1 to 2, 2 to 3, 3 to 4, and 4 to 1. But in actual practice, it gets slightly, okay. Now if you see the process 1 to 2, okay, isentropic process is there. So that is slightly towards the that dome side. Okay, so we are getting the not straight line. This is a some incline point. Then again we are getting point number 3. Okay, it is somewhat downward direction. Okay, irreversible. That first 1 to 2 is the irreversibility in the pump. So due to that, we are getting the this pattern. Now irreversibility means what? During the this all four component, result of the irreversibilities in various components occur, and friction, fluid friction, and heat loss to the surrounding are the major two components of this irreversibility. In the ideal case, we have neglected order the friction or the heat loss, but in actual case, we need to consider that heat loss as well as the friction occurred in the cycle. So due to these two reasons, our process may get in irreversibility. Okay, so due to that we are getting this pattern. Okay, now this fluid friction which causes the pressure drop, okay, in the boiler. So due to that we are getting the, so if you see the in the point number in the second diagram, okay, 1 to 2, so that is a 2s, that is our ideal point, or that is your ideal Rankine cycle. But due to the friction loss, okay, which causes the pressure drop, so where we'll get the new point, that is a 2a. Okay, so this is a new point. Okay, and due to this friction pressure drop, as a result steam leaves the boiler at a somewhat lower pressure, so that is a pressure drop. And also the pressure at the turbine, at pressure at a turbine inlet is somewhat lower than the that of boiler exit. So due to pressure drop in the connecting pipes also. So new point we are getting also at 3. That is a 3. Now again the pressure drop in the condenser is usually very less. So you can see here also at 4A, that is a new point. Okay, here also pressure drop occur, and water must be pumped to the sufficiently higher pressure than the ideal cycle. Okay, that is at point number this 4. So due to this, we require high pump and high work input to the pump. Okay, that is a 1 to 2 process. So again, other major source of irreversibility is the heat loss. Okay, from the steam to the surrounding, there may occur heat loss as a steam flow through the various components. Their heat loss occur. Also, and to maintain the same level of the net work output, more heat need to be transferred to the steam in the boiler, and to compensate this of these undesirable heat losses, our cycle efficiency is going to decrease. Okay, due to heat loss or the friction, fluid friction, our cycle efficiency is going to decrease. Okay, so due to this irreversibilities, our pump sorry, our cycle efficiency is going to decrease. Now, of particular importance are there irreversibility, which is occurring within the pump and the turbine. So the pump, it requires a greater work or greater work input, we can say, and the turbine, which are the produces the a smaller work output as compared to the ideal case. Okay, so due to the irreversibility. So under ideal case, what are the fluid flow through these devices is the isentropically. So here we can calculate actual pump and turbine efficiencies, and that should be isentropically. Okay, using the this formula. So here using the actual process, you can find the isentropic efficiencies of pump and the turbine. Okay. Now how this efficiency calculated? Very easy. At actual case, what was the work input to the pump, and at ideal case, what was the work input to the pump? So as we know, the output input, input will be the work input to the pump in ideal case divided by the at output case. So at actual case. So WS is the work input to the pump at ideal case. WA is work input to the pump in actual case. Again, from the diagram, we look at the WS means what? H2S, that means the ideal case minus H1 divided by H2A minus H1. Same procedure for calculation of isentropic efficiencies of the turbine. Okay, work output in the turbine at actual case. Now remember, at actual case, our output is that work output is less, so that I consider as a output WA divided by WS. And here also you can use the H3 minus H4A divided by H3 minus H4A. Okay, now this problem formula we got from this diagram. Okay, which is very easy. From this TS diagram, you can easily calculate the WS or WA. Okay, in case of pump as well as the turbine also. Okay, so this is the isentropic efficiencies of the efficiency of the pump. Okay, and this we got in case of the actual power cycle. Okay, now please write on this only formula. This formula is so useful. Please write down only formula. Sorry. Also this diagram also. Actual case. What will the diagram? This first. You can draw the diagram number B. B diagram you can draw. No problem. Don't draw that diagram A. Only diagram B and the formulas. Once again, I repeat, due to the fluid friction during the processes and due to the heat losses, irreversibility will occur, and due to that, our pressure drop will happen. Okay, so due to that pressure drop, we'll get the 2A point and 4A point. Okay, please write down. Draw the diagram, that BTS diagram, and write down the formula of the isentropic efficiency. Are you writing or not? Say yes or no. The PPT of this all lectures, you will get no problem. And also here I want to mention that what are the diagram. Okay, you should know the uh, resources of this PPT. So what are the material I have considered for the theory lecture? Theory. This data or this diagram or this formula I have taken from the basics of thermodynamics book of Eunice Fingel. Okay, Tata McGraw publication, Eunice Fingel book. Okay, That book also I will give to you also. Okay, for the basic understanding. For gate and other questions. Okay, there I will mention the materials, link of the material. Okay, don't worry. But for the diagram, okay, because in different book you will get the different notification, but pattern of the diagram or pattern of the, or curve will be same. This notification it may differ in the different diagram, different book. So the material which are I have used for this PPT or for my lecture, it is from the Unisingel book. Okay, thermodynamic approach by Unisingela. Okay, now here I will take one simple question which is asked in the IES 1994. Okay, IES, sorry, IES, here IES is there, 1994. Now, the question is correct representation of simple Rankine cycle on the TS diagram. Okay, now look at the option. Option A, B, C, D. Okay, now from these all four representation of the TS diagram of Rankine cycle, which is the correct representation of TS diagram of Rankine cycle, that you have to give the answer. Look at diagram and in comment box draw the please hit your answer or shoot your answer. Okay, Prajwal is saying answer A. Okay, Ganesh also Mir okay, Celine. Okay, yeah, correct. Okay, very good. So just will learn the pattern of TS diagram of Rankine cycle. So answer number A is the correct. Okay, you can see in the slide also I have mentioned. Okay, now let us move for the further one. Now second question. Now this question is asked in the IES 1999. Okay, now I will read the problem statement. Consider the following processes. Consider the following processes. Process number one is the constant pressure heat addition. Second process is adiabatic compression. Third is the adiabatic expansion. Fourth one is the constant pressure heat radiation. Constant pressure heat radiation. Now, the correct sequence of these processes in a Rankine cycle is, you have to tell correct sequence of processes in a Rankine cycle, which is the correct answer. Okay, look at the option number one, sorry, A, B, C, D, and tell or shoot your answer in the comment box, which is the correct. Okay, a main student has given answer D, and that answer is correct. Sorry, that answer is wrong. Okay, now just recap or remind the processes. First process is compression happens in the pump. That is the isentropic compression in the pump. So compression means what? Process number two. So just look at the option number B and C. There will get the first process the adiabatic compression. That means the isentropic compression. No problem. So now you have to eliminate the option number A and D. From B and C you have to choose a one option. Next, go for a remind. After compression, there is a heat addition process, and that heat addition process is a constant pressure. So constant pressure heat addition is the option number A. Now look at the B and 2 again. 2A. That means the same process as A. Then after heat addition, there is an expansion in the turbine. Here expansion means what? Isentropic or adiabatic process. So three is there. Sorry, 3 process is there. Adiabatic expansion. So if you look at the option number C, you will get the all processes. First is adiabatic compression, then constant pressure heat addition, then adiabatic expansion, and constant pressure heat rejection. Okay, so option number C is correct. Okay, here I have given the answer, and also I have explained all the process 1 to 2, 2 to 3, 3 to 4, and 4 to 1. Okay, Got it? Now okay, we'll proceed for the further point. Now we have up to this we have covered the ideal Carnot cycle, then modification of the ideal Carnot means the ideal Rankine cycle, and we have seen the actual pattern of the Rankine cycle also. Now, if we want to increase the efficiency of this Rankine cycle, what parameters we can consider, or how we can increase the efficiency of the Rankine cycle, which are the different parameters that we have to see. Okay, so here I mentioned different methods to increase the, or different parameters to increase the efficiency of Rankine cycle, and the first parameter is by lowering the condenser pressure you can increase the efficiency. Now how this by decreasing or by lowering the condenser pressure we can increase the efficiency, that I will explain. Now, as we know that steam power plants are responsible for the production of the most electric power in the world, and even small increase in the thermal efficiency. Now, why I am explaining this? Because if you increase even 1% of the efficiency, that is also helpful for us, because all the steam power plants in the world are responsible for the generation of the electric power. So by increasing the small percentage of the efficiency, that is also increase the power generation, electric power generation. Okay, and also it may save the fuel requirement also. So therefore, we have to take the efforts to make the increase of efficiency, or improve the efficiency of the cycle. Okay, okay. This cycle means what? All the power plant will work on this cycle only, or will operate on this cycle. So basic idea behind all the modifications to increase the thermal efficiency of the power cycle is the same. Okay, so what are the basic ideas is there? Okay, for the modification in the cycle, for what purpose? To increase the thermal efficiency are the same. So by increasing the by decreasing or by lowering the condenser pressure, you can increase the efficiency, or by increasing the average temperature at which heat is transferred to the working fluid in the turbine. That also another aspect that I'm going to explain. So now first I will explain the this point by lowering the condenser pressure. Okay. Now as we know that steam, what are the steam exist as a saturated mixture in the condenser, because after leaving the turbine we are getting the mixture of the saturated, liquid and vapor. Okay, at the exit of turbine, but at condenser we are getting the saturated mixture of the steam. Okay, at the saturation temperature, which is corresponding to the pressure inside the condenser. Correct? Please note down that at saturation temperature, which is corresponding to the pressure inside the condenser, we are getting the saturated mixture of the steam. Therefore, by lowering the operating pressure of the condenser, okay, by lowering the operating pressure at condenser means what? By lowering the condenser pressure at the condenser, automatically it will lower the temperature of the steam. Okay, automatically it will lower the temperature of the steam, and thus temperature at which heat is rejected is going to decrease. Correct? Because in the condenser we are rejecting the heat. So by decreasing the pressure, okay, where saturated, operating pressure, our saturation temperature corresponding that operating pressure, that is also going to decrease, and due to that temperature, where the heat rejection will happen. Okay, so the effect of lowering the condenser pressure on the Rankine cycle efficiency, that I have explained, I have shown the diagram, so you can see here in the diagram also what I did, that 4 to 1 pressure I have decreased. Okay, so we'll get the new saturation temperature. Now please note down, here I have decreased the condenser pressure, condenser pressure, so that by decreasing the condenser operating pressure, corresponding saturation temperature is there, no, that is also going to decrease. Okay, so that we are getting the new point, that is a 4 dash and 1 dash, and whatever the heat rejected is there, or heat rejected in the condenser, will get the by new area, and that is colored here, and that area means a, okay, as we know that if you increase the area of this curve TS diagram, automatically we'll get the higher efficiency. Okay, because this ERM is not our thermal efficiency. So by increasing the area, we are getting the higher, or by we'll get the increase in the efficiency. Okay, so this color area on this diagram, it represent the increase in the net work output, net work output, as a result of how it increase the area, by decreasing the pressure. By decreasing pressure means what? From P4, I have decreased the pressure up to P4 dash. Okay, P4 dash. The heat input required also increase. Okay, and heat input means what? At point number one. Okay, that is also going to increase. Here I have represented by the area under the 2 dash and 1 dash, sorry, 2 to 2 dash, because at 2 we are giving heat input to the boiler, so that is also going to increase that heat input. Okay, now work output work, that is the, now just a reminder, remind that our efficiency formula is W net divided by Q in. W net is increase and Q in also increase. Okay, so slightly our efficiency is also going to increase. Okay, now here increase is very small. Okay, because W net is also increased, and our heat input is there, that curve 2 dash to 2, that is also increase, so that increase is very small. Thus the overall effect of this lowering the condenser pressure is slightly increase the thermal efficiency of cycle. Okay, got it? How it is increase efficiency? Okay, so now if it take the advantage of this increased efficiency at lowering the pressure. Lowering the pressure means what? Condenser pressure. The condensers of the steam power plant usually operates well, okay, below the atmospheric pressure. So this does not present a major problem since the vapor power cycle operate in a closed loop. Okay, have you got or not? Say yes or no. If you, this area under the TS diagram is what? Our work output, correct? That is the W net. So if we increase the area, automatically W net will increase, and W net is increased means what? Thermal efficiency is increase. Okay, that's simple. Okay, say yes or no so that I can proceed further. Okay, Now, here we have to take one, or we have to consider one important point that whatever our condenser pressure is there, no, that we should not lower below the saturation pressure. Here I mentioned this condenser pressure is whatever the plant is there, it always operates below the atmospheric pressure. So whatever our peak condenser is there, that cannot be lower than the saturation pressure, which is corresponding to the our temperature, okay, of the cooling media. Okay, so by lowering the condenser pressure, it creates the possibility of air leakage into the condenser. Okay, and also by lowering the condenser pressure, increase the moisture content of the steam at the final stage of the turbine. Okay, so this one also we need to consider. So presence of the large quantity of the moisture in the steam is highly undesirable in the turbine because it decreases the turbine efficiency. How it will decrease the turbine efficiency? Because by increasing the erosion at the turbine blade. Okay, so we should not or we cannot lower the P condenser, that is a condenser pressure, lower the saturation pressure. Okay, saturation pressure, below that saturation pressure we should not go. Okay, so that point we have to consider. Okay, so this is the one point about the method to increase the efficiency. Okay, got it. Now remaining 3 points I will cover the in the next lecture and we'll go for the further point. I am teaching a theory part as well as some questions. Okay, okay. After learning all points, uh, problem also because this is important. Okay. Now, time being, please draw this diagram. This is important. Just write down the lower in the condenser
Yes,
pressure
sir.
to increase. Yes, sir.
Once your lecture
Hello,
is
correct,
over,
sir.
after
Okay,
your lecture, I
okay,
am going to continue.
okay, no problem. Now, students, here I will stop here. Okay, so remaining part will cover because Kai sir want to continue. So, have you got today's point? Say yes or no, so that I will conclude. In comment box, you can say yes or no. Okay. Thank you, guys. So here I will conclude. Tomorrow we'll say another point. Kai sir, you can continue now.